This one's hopefully going to be short. Sometimes these take a really long time. I don't know why. So let's just run this. It's just a printy demo. It doesn't do anything too crazy. Just going to talk about the features I've been doing lately. The first one, which is normally it's trivial enough that I wouldn't demo something like this, but it's for people who have been following along, I want to make sure they don't get confused by stuff they see next. So the first thing I'm going to say is that the syntax for enums has changed from what you've seen in previous streams. There used to be a C-inspired syntax where you put commas between the items, and there was like 1 colon. And now it's just this. It looks like, hey, name, colon, colon, value, or just name, semicolon. And the reason for the name, colon, colon, value is just because there's no reason you shouldn't be able to paste stuff into and out of enums. So if you were being lazy for a while, and you didn't make an enum, and you just had a bunch of constant declarations at top level like this, and then one day you decided to make this an enum, you should just be able to say whatever is an enum, and just do that and be done with it, right? You shouldn't have to like go in there and change the commas to semicolons and the 1 to 2 colons, and that's just a pain in the butt, and there's no reason for it, right? So the syntax is now that those just look exactly like constant declarations. And then if you're using the thing where the enum automatically increments the value, then you just don't put the value, right? And that works still just like C does all other ways. It's just, of course, the syntax is different. So if we come over here, so I say here I'm using fruit, which is this enum, and I say x is papaya plus 1. This is an autocast because normally this would give you an error. Adding 1 to an enum, 1 is not of an enum type, so it would complain about that. But you just say whatever, just make it work with autocast. And so papaya plus 1 gives me mango, of course, and that's what I have here. Now recall our print statement prints out enums by name. That's going to be important in the next section that we look at. Right? If I want this to be an integer, I can cast it explicitly to an integer in the print statement like I do down here. So I say, what's Nolly healing fruit? And I cast Nolly healing fruit to an int so that I get the integer instead of the name. And that's going to be it's going to be the next one after grapefruit, which is 86, right? So this is the way that enums have worked the whole time. It's just a different syntax, but it's just like C where it'll auto increment. And if you skip forward, it'll auto increment from there. Okay, so the new feature is that now we have an enum specifically for flags. So instead of saying enum here, because flags are a thing that you put in enums all the time, right? And in C++, it's really annoying. You have to like auto designate the values or whatever. So here, we have a new thing where you say enum flags. And again, you can specify the base type of the enum, just like whatever. And here, I've just let the compiler auto pick all of the values for these. I'm using the flags, and then I'm going to print out the first 4 here, and I'm casting them to int. So instead of seeing the names, we see the int values. And we see here they're 1, 2, 4, and 8. So when you have an enum flags, the way of picking the next value is just by doubling the previous value, right? Powers of 2, so that you can flag them together. Now, one good thing about this is that the print statement, or the print function that you can use, understands enum flags and can print them out in a useful way. So here I'm declaring a flag, lowercase flags of type uppercase flags. That gets the default value, so it's going to start at 0. So we see here 0. Let me get both of these at the same time, actually. Side by side. So then this was 0, right? So that's 0, that's 0. And then I OR FC, whatever the value of FC is, and then I print it, and it says flags is FC. And then I OR FA, and I print it, and now it says flags is FA or FC, right? I OR in FD, and I print it, and now it says it's FA or FC or FD. Now notice that the order here is different from the order in which I'm ORing them, but that's just because, print doesn't know what order I ORed them. It just knows it's a number. Down here, I ORed casting to type flags this arbitrary integer that goes way beyond what we defined, right? And I print it, and it says, well, it's FA, FC, FD, and then FG and H, and then also this number that was not included in any of the previous flag values, but we need to say it, right? So that is very useful and very nice. It makes flags much less annoying than they are in many languages. Now, just like in the regular enum case, you can define these values at any time. So here we've got these other flags. GA is going to be 1. By the way, we do start at 1 instead of 0, because you don't, for a regular enum you start at 0, but for a flag you don't really want a flag 0. That's just confusing because it won't work. All right. So here we say GA, GB, GC, GD. That's going to be 1, 2, 4, 8. And then here we've jumped to OX 1, 0, 0, 0. So then you can guess what GF, GG, and GH are going to be probably. So here I print GD, GE, and GF, and they're 8, right? Because that's 1, 2, 4, 8. And then I skip to this, and it's like, oh, that's 4096. And then the next one is, of course, 8192. So that totally works as you would expect. Now, in this list, you can put arbitrary numbers. Like you could put a bunch of numbers ORed together if you want. But you could also make a mistake if you're doing that. And so what happens if the compiler, like if I stick my grapefruit as 85 in here, and the compiler tries to auto-increment that for the next flag, well, it'll complain, right? It'll say, hey, the declaration is trying to use the next value in an enum flag sequence, but the previous value is not a single flag, it is OX55, right, or integer 85. Maybe I should print this in integer if you gave it or in decimal if you gave it a decimal, whatever. But actually, I believe, I haven't actually tested this, but it should work if I do it there. Yeah, because it doesn't need to auto-increment this. So it's like, that's not a single flag, but it's fine. You can do that if you want. It would be nice if enum flags added a flags.none. Well, you can use literal 0 for flags.none, right? Like there's no, if you want the name none, you can put that there. But the literal 0, so here when I said numbers don't cast to flags automatically, you have to cast it. That's true unless it's 0. If it's 0, then it's automatically any enum. Okay, so that's that. Next part of the demo, union test. So prior to today, we didn't have unions, right? I demoed a long time ago this thing called the place directive that tells you where in a struct you want to co-locate something in memory. So if I had the struct A, and it's got a type tag at the beginning that like maybe we're using to know what's inside A, like which members, because all these members are going to land on top of each other in memory, just like a union from C, then we need to know which ones are valid and which ones aren't. So here I've made this thing of type void, which is legal here. It's not legal in C, I don't think. It certainly didn't used to be, and I think it still isn't. But we can use this to say this is of size 0, and we can just use it to say, well, just put somebody there at that place. And we've got a radius that's a float, an account that's a signed 32-bit number, and a name that's a string. And whichever one of those we're using all depends on what's here. And then say, OK, we're done with all that. So after the name, put this position and angle, right? The problem with this is very useful in some cases, and we can talk in a little bit about why that's useful. But for cases like this, it's actually dangerous and error-prone. And the reason is the following. Suppose I just decided to reorder my members for readability. All I did was I took this name, and I moved it up to be the first one, right? So now the string is first, and the float, whoops, I changed this from radius to distortion, but whatever, there's a float. Let's change that. There's a float. And S32, right? I just moved the name up to the top. The problem is that the name is bigger than the other members, so by the time I'm done with this count, I'm still inside the name, and now these later members that aren't supposed to be part of the union overlap with the name. So if I print size of A and size of B, they come out different. So size of A is 36, but size of B is 24 because things are overlapping when I didn't want them to, right? And the reason that's happening, again, is just because this guy is bigger than the other guys. But it's not obvious that reordering this is dangerous. And so for that reason, we now also support C-style unions, right? I can do it like this, where I'm saying using u colon whatever, or it can be an anonymous union. And so in this case, it's also much more readable. I've just put these things, actually we don't need this here anymore. I've just put these things all in one group, and now you don't worry about it, and it goes to the bottom. So, so now size of C is the same as size of A. It's 36, even though I moved name up to the top, right? So I believe we're going to keep, oh, this comment is, let's delete this comment. That was some old code that comment was referring to. Anyway, so I believe that we will keep both facilities. We may add some features to the place directive to make it more useful in more situations. The place directive is useful when you want to maybe pack a type tag or some other things in a way that defies conservative, weird alignment that the compiler might do. And a union is something that you might want to use when you're totally fine with padding this out to whatever alignment that you want. We'll see how that shakes out. Okay, so like I said, that union was anonymous. Unions don't have to be anonymous. You know, I can just the way I could name a struct type before, I can name a union type. A union is only a struct where all the guys land at the same place in memory, right? So, so here I've got a union called stuff, and I'm saying size of stuff is whatever, and where are we? It's 16, and the reason it's only 16 is because a string is 16, and these are all smaller than that, but we pad out to the size of the biggest member, right? All right, so now I'm going to set the name to sailor, right? And I print stuff.name just to prove that the union works. So I print stuff.name, and it says stuff.name is sailor. And I say stuff.c, and it's 6. And the reason it's 6 is because that's the length of sailor, because the name, the first value in name is the length of the name, and the second value is the pointer to the name. And the length, since this is a little endian machine, it's an 8-byte integer, but the lower 4 bytes is the lower 4 bytes of the length, and so this signed 32-bit value captures that whole thing because it's only 6, right? That fits in 1 byte, much less 4 bytes. So, you know, that's just showing that we're correctly reading the value out of the union. Unlike some other languages you could name, unions can have constructors. I put constructed thing at global scope instead of right here because I wanted to use it again later in another example. But so here we have this thing called constructed thing. It's got some members, but it's also got a constructor that says, well, map A to float32 infinity, right? This, if you haven't seen the quick lambdas, this is just a polymorphic routine where the type gets inferred as needed. It's still strongly typed, just like anything in C or C++. Because this is a constructor, it just, the type of X becomes pointer to constructed thing, right? So then we're just saying that A is float32 infinity, right? So now, so we instantiate this, we take the size, and then we're going to print A, and we're going to print C. And now C overlaps with A again, and they're the same size, so what do we see? Well, we say the size of constructed thing is 8. That's because a float64 is 8 bytes. Thing.A is inf. That's how we print out infinity. And thing.C is, well, if you know IEEE 734 floating point representation, then you recognize this number. It's the hex representation of positive infinity, right? So that is that, union with constructor. You can declare a union in any scope, including a procedure or a top level. Again, that's not a big surprise. In C++, you can do that. In C, even, I think you can do that now. I don't know, probably. But, you know, here I'm just saying union, elephant, pelican, and so the result is these are both local variables of this procedure that overlap with each other, right? So I could say, I can do that same length trick, except I'm doing it with 64 bits now, but same thing. So elephant says, unfortunately, there's a radio connected to my brain, and then pelican is going to be the length of that string, which is 53. And then same with enums. I can make an anonymous enum, and if I do that, then I'm just using it, and all these values are pulled into local scope. So without explicitly saying using or anything, I can just say that and say CC is whatever, 2. So some of this is just like in C or C++. Some of it is not like in C or C++. All of it is relatively new over earlier versions of the language, so I just wanted to hit all that. Okay. Next, anonymous structs. This is a syntactic expansion of the language. You didn't used to be able to do this following thing. You used to have to name a struct type. Now I can say, here's some variable s, and what type is it? Well, it's some type struct that has a float called f. I didn't name the struct type, right? And that works now. So I can say, well, what's the size of s, and what's the type of it? Well, it's 4, because it's only got a float. And the type of it is, well, anonymous struct, because the print statement doesn't really know. Actually, the print statement probably can tell you what file and line this was defined in. So if we don't think it's too verbose, we might put that in there. Same with an enum. So I'm saying I can say E is some enum with this stuff, and so that it'll be the default value, which is 0, which is the first member. So it's alpha, and then I set it to gamma, and then there, right? What do I want to say about that? This is not really anything fancy. This is actually how enums and structs worked in original C. Like in C, you didn't used to be able to name these at all within the construct without adding a type def around it. But for the way that I program, I usually use name, struct, and enums, but it felt like the language needed to be able to handle them anonymously, and so that's fine. Now, this is relatively mundane so far, but it starts getting a little bit more cool when you remember that types in this language are first-class values as they are in functional languages, even though this is a fully compiled, statically typed language. So you can create and pass anonymous struct and enum types by value, and you don't have to give them names, right? So first, I'm just going to make this procedure f. It's polymorphic. It takes a variable called t of some type, and so the argument is a type. We don't know what type it is. We print what the type is, and then I get the type info. If it's an enum type, then I print enum, and otherwise I print struct. And those, because I didn't want this code to be really long, I put those out of line, but we can jump to them at the end of the file. They just go over the members and print all the members, right? And this is just using the type info introspection system that you probably have seen many times before if you follow these. If you don't, there's a presentation on YouTube that talks about how they work in great detail. Okay, so I'm going to call f on the type constructed thing, right? That is, remember, that's this guy that had this constructor. And when I do that, it's going to say, well, the type is constructed thing. It's got a member called A, a member called B, and a member called C. We're not printing the values of the members because we don't have an instance. We don't have any values for those members. We're just printing the type, or we could print the types of the members. Let me do that for struct. Oh, no, let's not do that, because I don't remember. I just don't remember what the routine is in print. Let me see. There's print type to builder. I'm not going to do it right now. Just because it's probably, where am I? It's probably, yeah, let's not do it right now. We'll do it later. We'll do it in the Q&A if we care and if I'm not tired. The reason is just if you print a type, then that's fine. But if you have a pointer to a type info, that's a different thing. And so I need to call a procedure to do that. And I have a procedure to put that into a builder, but I don't necessarily have one to do it here. And if this print sees a type info, it'll print the contents of the struct type info and not the actual type. Like the default behavior is not exactly what we want. Okay. Anyway, so why is that cool? Well, instead of just passing a name type, I can just make an arbitrary type right here. So here I'm going to call f on some new struct type. And what is it? Well, I don't know. It's got a position that's got a vector 2. It's got a bitmap name that's a string. And it's got a radius that's a float. And that just works. So t is some anonymous struct. It's got a position, bitmap name, and radius. And then, of course, instead of using this form of the declarations, I can use the form that gives things default values. Again, even though this has numbers, this is still not an instance. This is a type that if you instantiated it, would have an instance with these values in it, right? But the type doesn't have those values in it. It just has these members of these types, right? Now again, this could look confusing. Well, let's go here again, right? So again, it's an anonymous struct with members x, y, and name. So this really has no analog in C or C++. I mean, maybe in C++ you can do some very painful template things, but here it's built into the language semantics. So this is just fundamental, and it just works. So that's very nice. Again, that also works with enums. So I've got this enum with different values, and we print all the items in the enum. Now, why would you want to do that? Well, we've demoed before all of these ways that we can manufacture new types based on old types using, modify procedures and dynamic specialize and all that stuff. Well, I just want to show that you can pass this to something. I don't want to go, because it's off topic for this demo, I don't want to go rehash all that kind of type manufacturing thing. You can go back and watch those demos on YouTube. But just to show the basic idea, like I could have this instantiate and print routine that prints the type just like before, but then I can instantiate a value of that type. And the reason I can do this, even though it's a compile time, fully type checked, statically checked language, is that this argument, this $, means that we insist on knowing this argument lexically, right? So therefore, we can recompile this routine for any instance, any different value of this parameter, right? So we can instantiate this thing called value, which is of whatever type the type is, and then we can print it out, right? And so we call instantiate and print just on this struct type. It'll, again, print the type, and then that'll say anonymous struct. And then we'll instantiate a value, and we'll print the value, and the value will have initialized all the fields to all these values, and so we'll see all that, right? So here we go. T is anonymous struct. The value is x is 1, y is 3, name is hello. So that's all cool. And I expect this kind of thing to be very useful when it comes to just heavy use of generic programming or polymorphism or template metaprogramming or whatever your favorite name is for that kind of programming. Okay, now best convenient feature for last, something that people have wanted forever in C and C++. First, we're gonna just look at these declarations for a second. Someone asked if you mentioned the same anonymous struct twice, are they the same struct? No. There is no duck typing between things unless you make that happen yourself. So by default, any two struct descriptions are different types, even if they look the same. Can you pass a value of type struct x float to a function expecting an argument of type struct x float? No, because those are different types, actually. Anyway, okay. Last feature, and then we'll go to Q&A. So I've made here a simple system like you might have in a game where I've got some types of entities, right? Uninitialized, so I know if I forget to set the entity type. And then we have inanimate objects, we have doors, we have humans, and we have dogs, and whatever this game is or program or simulation that I'm talking about. The entity type is a 1-byte U8 thing. And then we're going to define what's our base class, but we don't really have classes, but it's a struct, right? And the type is going to be uninitialized, right? which then automatically makes it an entity type, right? That's the type of it, but we've elided the type and let type inference do that. It's got a position that's a vector 2. It's got like a bounding, center, and radius like you might have in a game. It's got a mesh name. And then we've got some arbitrary array of 3 values that are float, right? So that's all that is, something like you might have in a game. And then we've got a door and a human, and both of those have entity as their first field, and they're using that, right? So they're both compatible with type entity or whatever. They're, in C++, you would say they are subclasses of entity, except of course that we don't do vtables or any of that nonsense. And in fact, you can't shadow methods, or you can't shadow any kind of variable name automatically using this. Okay, so you may note some new things down here. So I'm saying a door is an entity, but here I'm saying, oh, but type equals door, right? But type is up here, right? Well, what's going on is that I can, any declaration that has a value that's constant, that doesn't require code that doesn't require code to run in order to declare what the value is, you can, sort of patch that in and say, well, this has an entity here, but the type field has the value door, right? And the mesh name has the value door default, and the bounding radius has 1. And by the way, buffer values, this is our crufty syntax for array literals that we're probably going to change. But we'll set buffer values to 1, 2, 3, right? So we can do all of this, and it doesn't require any code to run in order to happen. It's the same as if you had just pasted all these things down here and changed the values, which is something I've wanted to do in C or C++ for really a long time. So that is cool. And then in human, I have maybe some different, well, let's look at the printout to make sure that works. So here's door. It's got a base, which is an entity, and you notice that the type on entity is changed, right? And the bounding radius is 1, and the mesh name is door default. And the buffer values here, print only goes 1 level deep on arrays, so it didn't print these, but we print them out manually here, and they're 1, 2, 3. And then again, for human, we did the same thing, except we went as far as saying, hey, position.x is 5 and position.y is -5. That works, right? So it doesn't just have to be the name. You can sub-reference stuff. And in fact, you can subscript arrays and all this, right? For this to work, we have to have some equivalent of const expressions, like in C++. Like it has to be language semantically guaranteed that this is a constant that you can refer to without running code, right? So all this stuff, I don't think we ever demoed that, but you might have caught it on an informal stream before, that we implemented all this const expr stuff. So this gets reduced to 2 before, really before code generation even sees it, right? This gets reduced at the tree level. But then you can also, so the whole point of this is to do lightweight things without having to use a constructor, because constructors are annoying and stupid. But if you want to, you can still use a constructor. So here we have a constructor where we set the mesh name to human with a random number afterward. And so note that both of these things happen. So the position gets set to 5 minus 5, but the mesh name is also human 1. So if you saw the stream where we declare initializer and constructor and all that, these go into the initializer and these go into the constructor. And you'll note we set buffer values to 1, 2, 3, and then we set this to 7. This is a little bit of a conflict right here because we're doing 2 things, and strictly speaking, if you thought this was totally declarative, then these are saying to do 2 different things, because this says to set the third value to 3, and this says to set it to 7. But for now, I'm deciding we just execute these in order from top to bottom, and whatever you end up with is what you end up with. And we'll see if that's bad or good, but it seems okay to me for right now. Now, the one last thing that's a little bit maybe interesting to note is that door and human here are declared in two different places, which means it's just a test that this member setting works in two different contexts, right? This is at global scope, which means these values are set in the program image. So the compiler like pokes them into the global data segment during compilation time, right? Whereas this one, the initialized default values get filled out in code, right? Because the code here says allocate a human on the stack and then make sure all the values are the default values, right? So these two things are getting filled in totally different ways, but they both work, right? Okay. Now here I was doing this thing where it's sort of a subclass where you're using a thing, but that doesn't have to be. It can just be any field that's just in the struct can be initialized this way. So like here, I have a struct called bounding box, and it's not like a subclass of anything, but it has 2 points, P0 and P1, that are the lower left corner and the upper right corner, right? And here I'm just going to say I want P1 to be at 1, 1. We don't have struct literals yet. It's one of the things. I probably should have put that in on the roadmap of what we want to do before the initial release, but so I just set the members separately here for now. But you see, I declare a bounding box, and then I print it, and you see that P1 is at 1, 1. So that's nice. That is everything that I wanted to demo. So I'm going to take a 5-minute break. Then questions. Whoa, my font is too big. Back in a second.